Hi, my name is Eric Voigt and I'm the president of Rice Electric Vehicle for the 2018-2019 school year. Rice Electric Vehicle is an undergraduate design team here at Rice University which provides students with hands-on engineering opportunities to meet real-world challenges. This spring, we're going to be competing in the 2018-2019 Shell Eco Marathon Americas in the Battery Electric Urban Concept Division. Today, we'd like to show you around the car, our space, the mechanical and electrical systems we have on the car, and just take you guys on a little bit of a tour.
Okay, so this is the car we took to the 2018 Shell Eco Marathon, and the main changes we're moving on for next year's competition is that this car is a solid body frame, but then over here we have a solid chassis where we're going to mold the body around it.
So this is our chassis design that we built in SolidWorks and exported a model of here to weld according to this reference. We basically have two main frame rails going down the side with an assembly for the front bumper, a cabin area, and two almost box sections here to house the two rear wheels in here. We also have the main hoop for our roll cage, which is situated behind the cabin. And this will all be welded together out of steel square tube.
So this is our work in progress chassis as it stands. This is all made out of 1 inch by 1 inch square tubing with 0.0319 wall thickness, and all these joints are MIG welded together, and we finished these intersections by angle grinding them.
This is where the wheels are going to be situated in the rear. The motor is going to sit right around the rear section of the chassis on a metal floor, and the axle will have a 6:1 ratio from wheel axle to motor gear.
Our main front sub-assembly for the front suspension of the car. What I'm standing on right now, or squatting on right now, is the front bumper, if you will, and then we have two steering knuckles that we fabricated ourselves, held together by a 1/2 inch bolt, and it slides right off, revealing the bushing in the middle. I'll reassemble that real fast. And then these will be connected, linked together with a go-kart steering assembly that will link into each of these via some tabs we'll build off the knuckles. And when we're finished with this sub-assembly, we'll weld it to the rest of the chassis at points here and here.
I'm Louis Smith. We're the Rice Electric Vehicle electrical team, and we're here to show you the circuits that we built for the Shell Eco Marathon 2019 Americas competition. Manuel will start us off.
Hello, I'm Manuel, and this is our energy supply block diagram. It begins here with a 48-volt lithium-ion battery that's fused through a 40-amp fuse. It comes over here to a momentary push button, which can be activated by the driver to start the car. When that push button is pressed, the voltage will come down here, connected through an SP50 connector. It'll power up our buck converter, which will set that voltage down to 12 volts. That voltage could come back here through our three emergency stop switches. One of them is on the outside, one of them is accessible to the driver, and one of them is provided by you for the competition, the remote cutoff switch. It comes back and powers the contactor. Once the contactor is energized, 48 volts can flow through the contactor, through the SP50 connector, and then back to the rest of our circuitry. Now we can explain the rest of our circuitry. The 48 volts will come through an SP50 connector and connect to the motor controller. The motor controller is controlled by a pedal, accessible to the driver in the front. The output is connected through an SP50 to a motor to control the speed and the drivability of the car. The 12 volts of the buck converter also come out and go through the auxiliary circuit power distribution board. This power distribution board, it has switches that are accessible by the driver, and then the voltages go out to a light array of turn signals for the front and the back, normal on signals, and brake signals as well. There's a brake sensor here that comes also from the front of the car, where the driver would press the brake. And we have the outputs come here. There's also a wiper motor, and there's a horn. That concludes our energy supply block diagram. Now Mauricio is going to tell you about the motor controller that we've been building here.
Hey guys, I'm Sergio Mauricio, and I've been in charge of developing the motor controller for our car. Here's a PCB of it. On it we have a buck converter to power our microcontroller and our gate driver. And over on this side is where the magic happens. We have these two big MOSFETs that will allow us to switch on and off our current at a frequency of 10 kilohertz. And then this is the output to the motor, and then we have the input from the battery over here. It doesn't look great so far because we've been debugging it, and we're looking to have a new revision of this board early next semester to keep working on it and develop a very robust motor controller.
Hi guys, I'm Boyan from the Rice Electric Vehicle Electric team, and I'm going to introduce you to our testbed. So the purpose of testbed is to simulate the situation when the car is driving. So first we will connect the motor controller through this connector to this part of the testbed, and this is trying to simulate the motor part and the mass of the car. And then we'll connect to the other part of the testbed through this connector, and this is just to trying to consume the extra power that is left out by this part. This is basically just 24 parallel incandescent lines. Each of them is 200 watts, and it can maximally consume 4.8 kilowatts of power. And we can also control the maximum power it can consume through these switches.
Thank you guys so much for tuning in. We'll be updating our progress on riceelectricvehicle.rice.edu and our Facebook page. We look forward to seeing you in April.
Let's go, guys!